Okay, here we are starting with the second part of the online analytical processing, and the sections we are left with include the data warehouse design and usage, implementation of data warehouse, data generalization by attribute-oriented induction. When we think of designing a data warehouse, there are four different views that can be taken into consideration before we actually come up with the design for a data warehouse. The first one is called the top-down view. So as it says in the slide here, it allows the user uh, to select relevant information which is necessary to build your data warehouse. It mainly deals with the current and the future business needs, right, of of a business. It does not very much deal with the past processes uh, in the business. Then the next view is called the data source view. Um, it exposes the information captured, stored, and managed by operational systems. So we talked about the operational databases, right? The very raw data comes in through our operational databases. So the data source view gives a snapshot of that kind of data. Then we have our data warehouse view, which consists of fact tables and dimension tables. We already looked at what dimension tables are, what fact tables are. It also includes the various measures and counts that the different kinds of measures that we talked about in the previous section. So it also includes that about the data in this view. Then finally, we have the business query view. This basically sees the perspective of data in the warehouse from the view of an end user, all right? Of what is of interest to the end user is more or less is more important for the business query view. So in the previous slide, we looked at different perspectives that we can look at the that we can actually look at the um, data, data warehouse data as, or the different views that you can actually have of the data warehouse. And now we are going to look at various different approaches to designing the data warehouse and the process and the steps involved in the design of the data warehouse. So the first one we're going to look at is it's going to be either a top-down approach or a bottom-up approach, or it could be a combination of both top-down as well as a bottom-up approach. All right, so a top-down approach simply means that you start by designing every single thing about the database, have everything on paper, and then plan about which part to do by when, and you have a very extensive plan to go about building your database. So you already have your entire plan on paper and you just go about executing it. That's your top-down approach. On the other hand, your bottom-up approach says you start with small experiments, all right? You take small prototypes and you experiment with them and build on top of the working prototypes and throw away the ones that do not work. And basically this is your bottom up approach, and the top down approach is a more mature way of data warehouse design where you have the entire plan in place. But on the other hand, the bottom-up approach is a much more rapid approach of designing the data warehouse. Now, from a software engineering point of view, we can look at the same two approaches that we looked at uh, in the previous two bullet points, and we give them two different names. So the first kind of an approach they can follow is a waterfall model or a spiral model, right? So the waterfall model is, once again, it's more structured and it's a systematic analysis at every step, all right, before you go to the next step. So you have to have everything in one step, which is already the design is done and approved before you even proceed to the next step. All right. So that's your waterfall model. Then you have your spiral model, where you actually there is a rapid generation, just like the bottom up approach, where you're building smaller systems first, and then you basically you incrementally build on those prototypes. All right. As it says here, it has a short turnaround time because we actually first build a smaller prototype and just incrementally develop, and it has a short turnaround time and a quick turnaround time. All right. So that's your spiral model. So the typical data warehouse design process, the steps involved in it are: first, you have to choose a business process to model. Right. So what are you interested in? Orders, invoices, is it customer data? Is it product data? Is it sales data? So all one of these has to be picked out. Okay, and who does that? The client or the end user does that. Okay, then choose a grain or the atomic level of data of the business processes. So we looked at the different granularities that we can look at, right? The data. So we have to pick at what is the right amount of granularity of data we would need, right? Whether it's going to be a high level concept or a low level concept. Then we're going to choose the dimensions that will apply to each of the fact table records. Then we're going to choose the measures, all right? We looked at three kinds of measures, right? Algebraic, holistic, and there was another kind of data: algebraic, there was holistic, and distributive. Okay, there was algebraic, holistic, and distributive measures. So you also pick a measure that you would use to populate the fact table records. So now let's look at the recommended approach for data warehouse development. So we have two ways in which a data warehouse can be built. So one of them was having a data mart, separate data marts for smaller pieces of your data, smaller chunks of your data, or have everything together in an enterprise warehouse. We already talked about that in one of the previous sections. So we have distributed data marts, or we have our enterprise warehouse or our multi-tier data warehouse. Okay, and so basically, you use the data from either the data marts or your enterprise data warehouse in order to define a high level corporate data model. All right, and it's actually a closed loop feedback system for enterprise management. So after you build a model, you can actually further improve on the data which is stored in your data marts or in your enterprise warehouses. And once again, you design or you basically make some changes to the model, and that once again helps us improve on the data stored in your marts or the enterprise warehouse. So it's a closed loop feedback system, and this is a recommended approach for developing a good data warehouse. So the basic uses of data warehouse can be looked at in an incremental fashion. So there are three main kinds of data warehouse applications. The first one is the least complicated, which is just simple information processing. In this application of data warehouse, it just has to support for querying and some basic statistical analysis and some reporting, right? And some kind of visualization of the data in probably forms of crosstabs, tables, charts, and graphs, right? The current trend in the data warehouse information processing is to basically enable a low-cost web-based accessing tools, which are then also used along with web browsers, right? Which can also be integrated with web browsers. So information processing is one of the most basic and the least complicated applications of a data warehouse. The next one we look at is analytical processing, so which is one step up from information processing. It supports some more complicated operations. So it basically works with multi-dimensional data, and it actually performs analysis on this multi-dimensional data stored in the data warehouse. It supports operations like the OLAP operations we looked at, such as slice and dice, drilling, pivoting, and such operations, all right? And these kind of operations can be operated on historic data. They can be either summarized or and detailed forms, or they can be less, they can be more granular, all right? So uh, it basically allows us to, the main thing that separates the analytical processing from information processing is it allows us to access and basically work on multidimensional data, right? Then the third kind of application is our data mining, all right, which is the most complicated of the applications listed here, which include support for basically looking for hidden patterns and basically knowledge discovery process is the main idea behind our data mining application, all right? Looking for associations, looking for correlations, and constructing some analytical models based on these patterns, associations that we mine from the data warehouse data, and actually make some predictions based on what we learn, right, from our knowledge discovery, and then presenting these results using some visualization tools. So if you look at this more carefully, so the data mining is the most complicated of the applications of the data warehouse, although it can be used for any of the reasons listed here, for basic information processing or for some basically analytical processing that just uses some OLAP operations or data cube technology. And then we have more complicated applications like data mining. So from online analytical processing to online analytical mining. So why do we have to move from the online analytical processing, which is giving us pretty powerful tools, and why are we moving to the online analytical mining now? So there are several reasons. So we have very high quality of data in the data warehouse after we have cleaned the data, got rid of the noise, and have the data perfectly formatted in the data warehouses. The quality of data is very high. Okay, it contains data which is integrated, consistent, cleaned data. Right. So the available information processing structure you already have information processing structure in place around the data warehouses, such as the open database connectivity. Then you have, I think OLEDB stands for uh, Open Linking and Embedded Database. Web accessing, there are other service facilities, reporting, and OLAP tools which are already in place. You can basically use them for data mining and look for more interesting patterns in the already existing data warehouse. Or you could actually do some exploratory data analysis of the multidimensional data which is provided to you in the data warehouse. So you can actually use the OLAP tools like drilling, dicing, pivoting, etc. In order to basically learn about new knowledge, right? And then you can do online selection of data mining functions. You can integrate and swap multiple mining functions and algorithms and tasks which are included in the mining part of our data, and basically use it on the data warehouse. So we actually are basically using this minimal OLAP functions which are provided to us and learning some new stuff about some new knowledge, right? Learning about some new knowledge, and that's why we can loosely use the term online analytical mining. Let's look at the next section, which involves data warehouse implementation. We um, looked at a data cube, how to come up with a data cube in one of the previous sections. All right. So the data cube can be viewed as a lattice of cuboids, all right, of smaller cuboids, which can actually a union of all of that would actually give you the entire data cube. The bottommost cuboid was called the base cuboid, right? And the topmost cuboid was called the apex cuboid, which only contains one cell, which, which does not contain any dimensions, and the bottommost cuboid contains all the dimensions, right? So how many cuboids, all right, how many such smaller cuboids can we come up with in an n-dimensional cube with the L levels? The answer is the total number of cuboids is basically Li plus 1, and we use a pi operator from I is equal to 1 to n. So this is nothing but, you can also say it is L of I plus 1, the whole thing powered with, let's say, n, powered with n, right? Where Li stands for the number of levels associated with a given dimension I, right? And T stands for the total number of cuboids that you can come up with. Now, let's look at how the data cube can be materialized, all right, or whether or not you need to materialize the data cube at all, right? So what is meant by materializing a data cube? All right, that means you take a smaller piece of the cube and actually physically store it in some place, all right? So that is called materialization of the data cube. So the materializing every possible cuboid in your cube is called full materialization, right? If you do not materialize any of those smaller cuboids, then it's called no materialization. And you have something in between called partial materialization, where you're only going to materialize certain cuboids which are of more interest to you depending on your data mining task at hand, right? Or you can say the cuboids which are being accessed more often can be partially materialized, and those which are not can be left out, right? So there are three types of materializations which are possible. The first one is full materialization, where you materialize every possible cuboid from the data cube. The second one is no materialization at all. You look at the entire cube and you have to access the entire cube even if you need just a small bit of data. Then you have partial materialization, where you're only going to materialize small some of all the cuboids and not all of them, depending on the interestingness of that some of those fewer cuboids. Right. So how do you do the selection of the cuboids that you want to materialize in case you want to do partial materialization? You can do it based on size. Say your data analysis deals with something to deal with the sizes of cuboids, all right? So all cuboids of a certain size can be materialized. Then we have sharing or access frequency, how many times a cuboid is being accessed. That's also an interesting way of finding out which cuboids to materialize. So, several data analysts have proposed that there should be a simple operator to actually compute a data cube, just like you have a grouping operation which already exists in your SQL query language, right? So they also proposed that there should be something like a cube by operation, right? So how can you define a cube? So you can define a cube with something like the statement which is listed under the first bullet, right? Let's say you define a cube on sales and you list the dimensions you're interested in, which are item, city, and year. Then you also list the aggregate measure, all right, which is sum that includes sales in dollars. And you can actually just simply say compute cube sales, and by uh, uh, basically defining the dimensions which should be a part of the cube, and the measure, you should actually get a data cube. All right, you should be able to form a data cube in your database. All right, if you actually transform what is in your DMQL, which is your data mining query language, um, you can actually convert it into an SQL-like language, but there is no cube by in which exists in SQL language. But this is what it would look like. It would say select item, city, year, right? And then sum of amount from sales, and you're going to have to cube by item, city, and year instead of saying group by. Okay, so this is basically equivalent to performing a set of group bys on let's say certain items taken together, right? Certain dimensions taken together, and basically you can actually come up with the cube by. So cube by is nothing but a set of group bys put together, right? So you have to let's say find the group bys of date, product, and customer. Date and product, date and customer, product and customer, date and product and customer just one at a time, and nothing at all, right? So this was our from our base cuboid to apex cuboid, right? The same way the group bys for city, item, and year are listed in the form of a lattice structure on the right side, right? So you take nothing at all, or you take city, just item, or just year, or you consider item and city, you can consider city and year, or you consider item and year, or you consider all three dimensions at the same time. Okay, so if you do a group by with all of these, that's when you're going to get an equivalent a database that you would get after a cube by operation. Now, in order to access or efficiently access the data in data cube, a lot of these data warehouse systems, they actually support indexed structures and basically materialized views, which we talked about, smaller cuboids, right? However, we are going to look at two other indexing techniques which are possible. The first one is your bitmap index, and the next one we're going to look at is called a join index. All right. So bitmap index, how does it work? It's an index on a particular column, on a one particular column, right? So every value in the column is going to be a new column. It's going to be mapped to a new column, and basically it'll be represented with a bit vector. All right. Why? Because bit operations are much faster than actual values. All right. The length of the bit vector is going to be defined by the number of records in your base table. Right? So the ith bit is set if the ith row of the base table has the value for the indexed column, right? It is not very suitable. This method of indexing is not very suitable, especially if you have high cardinality domains. So let's look at what it means. So let's say you have a base table with let's say customer ID C1 to C5, and you have a column called region, another column called type. All right. So the different types of values that the region can take are, let's say, Asia, Europe, and America. So there are three different values that it can take. So we are going to have three columns, all right? Instead of region, the index on region is going to have three different columns, all right? So you have the record ID, which is going to map to your customer ID. Then you have three different columns, which represents the region. And each of the values that the region can take become the column names, all right, and or the attribute names of the columns. And then you're going to have a one under that column if that is in fact the region, all right, for the given record, and zero if it is not. All right. So for the first record C1, right, the region is Asia. So the Asia column is going to represent 1, Europe, America are going to represent 0, right? Let's pick C4. C4, the region says it's America. So under America, it should be a 1, and under Asia and Europe, it should be a 0. Right. So a similar way, the index on type is shown in the next table. So you have record IDs mapping to the different values that the type can take. So there are two different values. The one of them is a retail, the other one is a dealer, right? So you just have two columns added to the index on type. Once again, so let's take C2. So C2 says the type is a dealer. So under dealer we see a 1, and under retail for the same row we see a 0. Okay. All right, so this is how bitmap indexing is done. If you have taken a database course before, a basic database course before, you must have looked into how you join two tables, right? So how the join operation works. When you have to join two tables, you have to have one column which is common in both the tables, right? And you actually apply a join operation in order to join the two tables, on, you say the join is on the common column, right? So in order to do a join index, let's say on our ID and SID, okay, so our ID belongs to let's say another a set of dimensions from R. SID belongs to another set of dimensions from S, right? You can do a join on both of them. Once again, just like the join operation from databases, you have to have a common dimension in between the two of them, right? So on the right hand side, you have a picture, right? You have a set of dimensions which include location and sales together. Then you have another set which include the item and sales. So you can actually join the location and the item to the sales, right? So it will actually help us materialize what is called a relational join or a tabular join file, and it actually helps us speed up the relational join process. Okay, in our data warehouses, so we have talked about the two-dimensional join, right, that happens in a relational database. So how does it work in data warehouse? The join index basically relates the value of our dimensions in a star schema to the rows in the fact table. All right, so the example is given on the right. You have the fact table, which has sales and two dimensions, city and product. All right. A join index on the city maintains for every distinct city a list of our IDs of the tuples which record the sales in the city. So the join indices can span multiple dimensions. So just like you can do a join on more than two tables, you don't have to do a join just on two tables. You can do a join on three tables. So the same way you can actually do a join across multiple dimensions. Let's learn about how we can go about doing efficient process of basically doing online analytical processing queries, right? So for that, it has to be done in two steps, right? First thing, we need to know what are the operations which have to be performed on the available cuboids, right? So which operations and in which order they have to be performed in order to get down to the smallest cuboid of interest to us, right? So we have to have that planned, right? Whether it's a drill down, drill roll up, right? And have the corresponding SQL in the OLAP operations. All right, so in an ordered format, the order is important in order to get to the size of the cube which is of most interest to us, right? Which operations have to be performed and in what order, right? So the next thing is determine which of the materialized cuboids which have already been materialized are actually useful to us. Okay, so should be selected for the online analytical processing operation. So first look at the already existing cuboids and figure out. So let's look at an example for that. So let there be a query to process on brand and province or state, and with the given condition that the year should be 2004. And there are four materialized cuboids, right? The first one is on year, item name and city. The second one is year, brand and country. The third one is year, brand, province or state. The fourth one is item name, province or state, right? So which ones should be selected to process the query, right? So the answer for this question, particular question, is the 1, 3, and 4, right, can be used. The cuboids in 1, 3, and 4 can be used to process the given query. Why is that? Because we know that finer granularities can be produced, cannot be produced from coarser granularities, whereas you can produce coarser granularity from a finer granularity. What does that mean? So if you have very detailed data, okay, so you can get less detailed data by, let's say, finding some measures, aggregating values, and get the less detailed data. All right. However, if we already have the sums and the measures done, and if you have the coarser data or the less detailed data, you cannot actually extract the more detailed data out of that. All right. So what we are interested in is brand. Okay. So what do we have? We have brand or item name. Brand is the same as brand, okay, the same dimension. Then item name is listed in two of the cuboids, which is of a finer granularity, so it's all right. Okay. The next one we're looking at is year is 2004. So in all the four cuboids, you have the listings in with respect to years, and the fourth one has, of course, its year data, and with respect to 2004, which is the data we are looking at, we are interested in, right? Now the third dimension says province or state. Okay, so the first one says city, which is going to be much more detailed data. Okay, all the cities in a state will be listed, which we can actually put together to get the state-wise information. The third one is province or state data. Fourth one is province or state data, which is the same dimension as the one we are looking for. However, for the second one, it says country. Okay, it has country-wise data, but we are interested in state-wise data. Right? If we have the country-wise data all summed up, we cannot get the state-wise data from the country-wise data. Right? However, we can get the state-wise data from the city-wise data by adding it up. Right? So the important thing to remember here is you can get less detailed data from the more detailed data. However, if you are given a cuboid which has a less detailed data, right, and you're trying to do a query which needs the more detailed data, you cannot pick the one which has lesser details. All right. So the online analytical processing server architecture can be designed in various ways. The four ways are listed here in this slide. The first one is relational online analytical processing. So basically just view it as kind of an extension of our relational databases, which contain tables in a tabular format. All right. Then the other one is your multidimensional OLAP, which is going to be your data cube technology, where you actually list it in the form of a cube. Then you have your hybrid online analytical processing, which is kind of a mix of the two listed above, which is your relational OLAP and your multidimensional OLAP. So it provides a flexibility. It can be low level, which is relational database, or it can be high level in the form of arrays or data cubes. Then you also have some specialized SQL servers, which basically provide some special support for SQL queries, which can be done over the star and snowflake schemas that we looked at. So the final topic in this chapter is data generalization by attribute-oriented induction. So that is going to be from now to the end of this chapter. So attribute-oriented induction is an approach for data characterization or to come up with a concept description, right? And it was proposed in 1989, right, in a KDD workshop. This process is not confined to categorical data. That means it's not a categorical data example is nominal or binary data, right? It's not confined to that kind of data, nor is it confined to numeric data or certain particular measures, right? How exactly is the attribute-oriented induction performed? Right? So first you collect the task relevant data, right, or your initial table using some kind of a database query. Then you're going to do what is called generalization, okay, by removing the attributes which you think are not necessary, and then you're going to generalize some of the attributes. You're going to apply aggregation to some other attributes by merging some identical attributes, right? And their counts, using their counts. And then finally, you can actually you come up with a table which has crosstabs, and it can be represented to the users. The knowledge that you acquire can be represented through to the users, and interactively you can work on improving this process. We are going to learn about attribute-oriented induction through an example presented here, right? So in the example, what are we required to do? We have to describe the general characteristics of graduate students in the university database, right? So how do you describe the general characteristics? So first you're going to fetch all, in step one, you're going to fetch all the relevant data using a simple SQL statement, all the relevant data with respect to all the students in the university, right? So what is going to be the relevant data? Name, gender, major, their birthplace, birth date, their place, the residence, their phone number, their GPA, right, from something like a student database, right? And what kind of student do we want? We only want the graduate students. We do not want bachelor students. So we pick only the students in the university who are, let's say, in MSc, MBA, PhD, if those are the only graduate programs offered at a particular university. Okay, then we're going to perform attribute oriented induction. We're going to look at that in just a little bit. Then we'll present the results of our generalization, okay, in a crosstab format, right, and give it to the user to understand. Okay, continuing with the example, we have the initial relation, which has the name, gender, major, birthplace, birth date, residence, phone number, and GPA. Okay, so among all these attributes, we know that the name and phone number are going to be unique for every single row in the table, right? Every single row in the table, they're going to have a unique name and they're going to have a unique phone number, right? So we are going to throw away such columns, right, which are actually going to come in the way of our generalization, okay, because they actually make every row unique, right? So you're just going to remove the name and remove the phone number. You're not going to learn anything new from those two. So just throw away the name and the phone number. Now what do you do next? So gender, it's already at a pretty minimum granularity, so we leave it as it is. It's retained. Then let's look at the other attributes here. Major is given as computer science, physics, etc. We can further generalize it by saying the major is in the field of science, engineering, business, right? Instead of listing what their exact major is, right? The next one is birthplace. So we're not really interested in their exact birthplace. So let's just retain the country and throw away the rest. Then we have their birth date. So once again, we are not interested in their exact birthday. We are interested in their ages. Okay, so we are going to decide on certain age ranges. Okay, and basically list them as to a tuple to belong to one of those age ranges. Okay, then we have our residence. Once again, we only list city, which is of interest to us. Everything else we throw away. And GPA, we once again create some aggregate some sets there, as in let's say something between 1 to 2 is a poor GPA, between 2 to 3 is an average GPA. Let's say from 3 to 3.5 is very good GPA, and let's say 3.5 to 4 is excellent GPA. Right, so if we create groups like that, you can actually put each of the row information into one of these possible groups, they based on the GPA that we have. So we are going to get a prime generalized relation as shown in the second table. So we are going to add an extra column which consists of counts, because after doing this generalization and removing the unique attributes, we're going to end up with rows which are similar. Okay, we're going to end up with several rows which are similar. So we are going to actually, instead of listing each similar row again and again, we're going to just count them and going to list the and we're going to list the count at the very end of every row. Okay. Now, one example of a crosstab table is listed, where we are only considering, let's say, the gender, and then we are looking at the birth region, okay, and we are looking at the counts, right? The counts which tell us if the gender is male, how many of them were born in Canada and how many were outside of the Canada. If the gender is female, the same information. So we're listing the count information that we gathered from our second table and listing it in a crosstab format. So if you remember, we saw a similar crosstab format when we were doing chi-square measures and correlations, right? Covariance and correlation. We had a similar table where we had, I think, gender and they play chess or not, right? And we found the chi-square measures in order to figure out if the two attributes had a relation. Okay, so from here we can actually use the crosstab format that we have come up with in order to find the relationship between the attributes. So this slide lists what are the basic principles behind your attribute-oriented induction. So the first one was data focusing. That is, you actually pick up the interesting data or the data of interest to you depending on the task at hand. Then attribute removal. That is, if you have an attribute which has all unique values, or it has too many unique values, you're going to remove that attribute, right? Because it's not possible to do a generalization on this attribute. Then we do a generalization on the attributes when you have uh, different values that the attribute can take and several rows have similar values. Then you actually can do attribute generalization. You have to do a attribute threshold control. That is, you have to make sure the generalization leads to basically a table in which any attribute value does not contain values which are more than 2 to 8. All right, so the number of values that a given attribute can take should not be more than, should be between 2 to 8. All right, then we have the generalized relation threshold control, which actually controls the final table size. The attribute-oriented induction algorithm mainly has four parts to it. The first one is basically getting the initial relation out, then the second part is basically deciding whether a given attribute should be removed or it should be retained. Then the third task is to perform the actual generalization, and the fourth task is to present the data that you have found to the user. The presentation is the fourth task. So the generalized results can be presented to the end user in different ways. It could just be shown as generalized relation, which was the middle table in that example, but it can also be shown as a cross tabulation, which was the third table in our example. Okay, and there are different visualization techniques that can be used, even with the cross-tabulated measures, such as pie charts, bar charts. There can be curves, cubes, or some other visual forms. So other than these two, you can also basically come up with quantitative characteristic rules. Basically, these are similar to some association rules, which we looked at a basic example in the first chapter. And also in the next chapter, we're going to see some association rules. Okay, so you can actually present the association rules and what you have learned about the association between the attributes, right? So that is how we come up with these quantitative characteristic rules to present the results or the information that you gathered after your attribute oriented induction process. So, minding class comparisons can be considered as a branch of the attribute-oriented induction that we have looked at. So, the comparison basically deals with comparing two or more classes of data, right? So, what is the method to go about minding class comparisons? So, you're going to partition the set of relevant data into, let's say, a target class and a contrasting class. If you remember the definition of characterization and discrimination, right? That was what our discrimination was. So we are right now looking at how to basically execute the process of discrimination, right? Then we'll generalize both the classes to the same high-level concepts, right? Then we'll compare the tuples which have the same those high-level concepts, and we're going to present for every given tuple the support, or basically the total number of tuples which support this data, and the comparison, or the total number of tuples in both the sets of data which are different. Okay, so something like this will also be used in our association rules, which we are going to cover in the next chapter, right? So now finally let's take a look at what are the similarities and what are the differences between the concept description and the cube-based online analytical processing. So what are the similarities? So both the processes use data generalization, and the presentation of data summarization is at multiple levels, not just a single level, right, of abstraction. And both of them are use interactive drilling, pivoting, slicing, and dicing of the data to get the relevant data first. All right, so these are the similarities between concept description and cube-based OLAP. Now, what are the differences? OLAP has a systematic pre-processing. It is much more systematic than concept description, and it's query independent, and you can actually drill down to a very low level, right? Uh, the the attribute oriented induction, on the other hand, has basically has automated the desired level of allocation, and you can actually perform the analysis even when there are several relevant dimensions. Then attribute oriented induction, it works on data which is not really in the relational forms, because we are actually generalizing and and coming up with different classes during our generalization process for attribute-oriented induction. So finally, let's summarize what all we have learned in the 2 video lectures of online analytical processing. So this slide summarizes what all we have come across in this chapter. So we started with data warehousing, defining what a data warehouse is, what are dimensions, what are the different measures, different schemas such as the star schema, snowflake schema, fact constellation to represent the data in the data warehouse, and what are the different kinds of operations that can be performed on a simple on a given data warehouse, such as drilling, rolling, slicing, dicing, and pivoting. Then in the next section, we have looked at the data warehouse architecture, design, and its usage. Then in the next section, we've looked at the implementation of the data warehouse, how to actually efficiently compute the cubes, how many cuboids to come up with, what is partial materialization, what is full materialization, what kind of indexing is possible. We've looked at bitmap index and join index in particular, OLAP query processing, and we've looked at 3 different kind of servers architectures. Then finally we have looked at data generalization process called the attribute oriented induction. So this slide and the next slide contain references of several papers from which the material for the chapter was taken. I guess with this we come to an end of the chapter of chapter 4 in your textbook, which is data warehousing and online analytical processing.